Hi guys, today we talk about integral tests, and this is for us to perform a series whether this series is converges or diverges. So if you're not known what is a series is like, say we have a sequence of number or a list of number, and we sum up all the number together until the term an, and this is called series. In sum of all the number is called series. And we need to determine whether this series converges, means it focuses at one point when it goes with the infinity term, or it diverges. And we're using this integral test to perform it. So before we do the integral test, there are some of the conditions we have to fulfill. Let me talk about the main concept of integral test. So let's say we have a series, a summation, and starting from 1 to infinity, and a term. And integral test, we need to transform this series into an integral, like this. From series, transform into integral. And we have to fulfill 3 conditions, all right? Remember this one, because not all series can perform integral tests. So it has to specify these 3 conditions. And first is whether this series is continuous. Or we say this function is continuous. So what is meant by continuous? Means that when we plot a graph, it is not stop. At any point, it is very smooth, it's so-called continuous. And what is mean for non-continuous? For example, 1 over x minus 2, where x cannot be equal to 2, right? Because when it's 2, we got 1 over 0, we got undefined. So let's say a plot graph like this. Then at 2 here, it cannot be at this place. It doesn't have the number at 2 because it goes infinity, go up, and continue after that. So it breaks at the point, which is 2. So that's why we can say this graph is not continuous. That's how it's so-called not continuous. And if it's not continuous, then we cannot perform this integral test. Right. So we go ahead, find the other condition, which the series has to be positive. So it means all the values should be positive, cannot be negative number. And the third condition, which is it has to be decreasing. So decreasing, you might be confused why is positive and decreasing. Decreasing means the number getting smaller. Let me show you an example. And let's say we have a series 1 over 2, 1 over 3, 1 over 4, and you can see here all the numbers are positive, right? So it's set like this, and it's getting smaller. 1 over 2, 1, 3, 1, 4, this is like 0.5, 0.33, 0.25. Can you see the number is getting smaller? And this is we so-called decreasing, or in the layman meaning is called smaller. When it satisfies all these 3 conditions, only we can perform the integral test, right? Remember, we have to test after condition, whether it's continuous, positive, decreasing, only we can perform the integral test, which we transform the series into the integral. So let's go ahead, we do some example. Let's say I have one example. Let's say it's just a simple one. 1 over n squared. All right. So we have to check whether it's continuous. So yep, it is continuous because there's no any point here. It should be continuous because n squared. Yep, this is continuous. And whether we see is this positive? Yep, because we put any number starting from 1, okay? It based on this boundary as well, n equal to 1, all right? So let's say starting from 1, I substitute 2, 3, 4, 100. I also get positive number. It also gives me a valid answer for any number starting from 1, all right? So for n is greater or equal to 1, is continuous, is positive. And will the number getting smaller? Is it decreasing? Yep, because when n increases, then this whole overall number will get smaller. Yep, it satisfies all these 3 conditions, and we can go ahead to do the integral test right now. So we transform this thing into an integral. We can change this n into x if you can change it is, let's say it's equal and become x squared and dx. All right. And this is from 1 going to infinity. Same like here, from 1 going to infinity. So we're changing from something discrete into something continuous. Right. If you find it's difficult for you to put x, you can put n as well. Is as long as you perform the calculation, you can do like this. All right. But some books they prefer using x, so I use x here. We just change, and because we used to do the calculation in terms of x. All right. And in this case, I'm gonna do, because I'm gonna put limit for something. I don't want to put the infinity here. I want to put here, let's say I put a number as b approach infinity. So right now here, I put a b, 1 over x squared, I can write in x power of -2, easier for me for later calculation. If you integrate this one, you should get -1 over -1. All right, and we got 1 to b and limit approach infinity. All right, okay, and then because no space here, I write on top here. Using different color. So I substitute b. All right, b inverse 1 over -1, and I have to minus -1 power of -1 over -1, and this thing is we get +1, right? Because negative positive. Sorry, -1 inverse. Sorry, it should, yeah, the whole thing here. I write it again. -1 power of -1 over -1. This one also inverse of 1 is we get 1 divided by -1 here, negative, positive, like this. So +1. And limit b to infinity. And since this is constant, I can take it out. Even I put infinity, it still get 1, right? So I put it here, 1 plus, this is minus, I can take out the minus, limit b over infinity, 1 over b. Right, I can do like this. So when b approaches infinity, means I have to substitute infinity here, 1 over infinity, and what we gonna get? We get 0, right? 1 divided by something very, very big, it approaches to 0. So just 1 minus 0, in the end we got 1. And this is our final answer. So we got the integral. So the integral is converges. And so for this series, it's also converges. Okay. Cool. We try another example. Example 2. Let's say we had to find this series, 1 over n squared plus 4. All right. So we're going to check whether we can perform the integral test. So we're to check whether it is continuous. So we look at here, n equal to 1. So for n is greater or equal to 1, I put any number here is still valid, right? It doesn't give me something 1 over divided by 0. So there's no such number here because it's square. It's always got positive. Unless this will get like -4 plus 4, 1 over, so 1 over 0, only then it's not continuous. So right now, is this continuous? Is the number positive? Yes. Is it decreasing? Yes. When n increases and the number getting smaller? Yes. All right. We fulfill all these 3 conditions, only we can go to perform the integral test. Okay. So we go ahead to perform the integral test, and we transform this into integral 1 over infinity. 1 over, I gotta put in x squared plus 4 dx. Haha. So you might see this involves some of the previous calculus knowledge, how to integrate this one. If you still remember something like this, if you integrate 1 over a squared plus x squared dx, we should get something like this, 1 over a arctangent x over a plus c, all right? So it's same for here. This a is just like 2 squared. So I'm going to get 1 over 2 arctangent x over 2 plus c, because this is a definite integral, so we don't have the constant term here. All right. So I'm going to write this down here. So if you get me, before this, I'm going to write, change it into limit. So I'm going to put limit here. I'm lazy. So I put here b approaches infinity. And this is not infinity anymore. I say this is b. And I integrate this whole thing. I will get 1 over 2 arctangent x over 2 bracket 1 to b. Okay, I always forget my limit. B approach infinity. Okay. Next, substitute b here and substitute 1 here, because 1 is constant. Then I would say limit. I would just take up the b here, 2 tangent b minus 2 and minus, because limit infinity, if I put 1, is nothing but just a constant term. So I just write this down, half over 2. All right. So this is the part which is make people feel very complicated. But no harm, we can put infinity here first. We can, no choice, we put infinity here, substitute the infinity. So as you remember, if what number, what tangent, what thing, we get at infinity. All right. You still remember? This is, which is the, at here, we get almost approaches infinity, which is pi over 2. So we can say tangent this one is equal to half tangent over 2 minus this one. You can use calculator to find it, but this is a constant term. So overall, it has a number. So it means that it converges at this number. Converges at this number. So when the integral, this integral converges, and therefore our series converges. And this is how we prove that it is converges. Okay. So I like to try this example on your own. You can pause the video a while and try it on your own. And you go to 2, go into infinity, 1 over n ln n square. Oh my God. Right, so remember, the first thing to check the condition, right? Remember to check the conditions. And remember, we're going to transform it into integral and see whether it converges or diverges. Okay. So in the end, you'll find this one is converges. Okay, let me show you how. So we try to see whether this is continuous. N has to be 2. And when n is greater or equal to 2, you can try this up. There are 2 methods to prove whether it's converges, diverges. You can sketch the graph, if you know how to sketch the shape of this graph. All right. It's going to be something like this. Oh, not touches, but approaches. Okay. And this is our graph for 1 over n ln n square. And as we can see, just away from this graph is continuous. It is positive because above the x-axis, all right, above the x-axis here is not below. So this is positive and this is decreasing, right? The number getting smaller, the y number getting smaller. All right, this one of method using graph. Another kind of method that you can expand this series to try this up. For example, I can substitute starting from 2, 1 over 2 ln 2 square, and add with another number, 1 over 3 ln 3 squared plus 1 over 4 ln 4 squared. Okay, so you get something 1.04 plus 0.28 plus 0.13. This one might be easier for you since you have a normal calculator. So yeah, this is positive, right? And we don't get any number which is undefined, and it is decreasing number. So it satisfies the condition to use the integral test. So we can go ahead right now to transform this series into an integral. So it's equal to integral from 2 to infinity 1 over x ln x squared dx. All right, and I'm going to make this infinity into a limit. Let's say b approaches infinity, and this is my b right now. Okay, cool. All right, and you think of how to get this thing integrated. So I can let something, the bracket, into a number. Let's say I let u is equal to ln x. So du dx is equal to 1 over x. Okay, and I change dx into du. So dx equal to x times du. I'm going to substitute everything here. So my dx right now changed to du, but times x du, right? And 1 over x remain. This will become my u squared. And x and this x can be cancelled out. So in the end, I will just end up like this. Integral 2 to b limit b approach infinity. So 1 over u squared is very simple, is equal to u power -2, right? Then I'm going to integrate this thing as normal. You can treat it like just like x. Then we got u -1 over -1. And to b limit b approaches infinity. All right. Okay, so right now we're going to put in the value b and 2. So since 2 is a constant, so I need to put the limit here. Limit only for the b. All right, is negative 1 over b minus my negative is becomes a positive, and u here is, remember we just now we let u is equal to ln x, so I become 1 over ln x, whereby my x is 2, here is 2, yeah, and b here I need to change it into ln b. Okay. Okay, so if we put infinity here, 1 over something infinity, we'll get 0, and then plus 1 over ln 2, so therefore the answer is just ln 2. So means that this integral converges as ln 2 when the integral is converges, and therefore the series converges. All right, so this is the video for you to learn integral tests easily. So if you think it's useful, remember to like and share or comment something below if you have any questions. All right, I'm going to see you in next video.